So to recap from last day, anytime you're doing a maximum or a minimum problem, you're saying what is the maximum amount without a precipitate forming, or you're saying what's the minimum amount to just begin precipitation. And what we're doing, hi. Do I have it? No. Okay. And what we're doing is we're saying we're going to be right at KSP. Because it's like we're unsaturated, we're unsaturated, we're unsaturated, we're unsaturated, we're saturated, but no precipitate, and then all of a sudden we're precipitating. Yep. So we just start to form a precipitate, same calculation. So you will be given KSP and A, you solve for B, or given KSP and B, you solve for A. So you're always going to have to identify the precipitate. The question will say precipitate. Or precipitation. And just like every other type of calculation question we have done to this point, you will write the C and write the KSP. In this particular case, you will plug in KSP. You will plug in one of the ion concentrations, and then you just solve for the other ion concentration. And it's so easy. The math is so easy. You'll be like, why did I get this question wrong? And it'll be because you didn't plug in two things and solve for the third. Maybe you said KSP is equal to x squared, right? And you solved for x. It's not equal to x squared because that's not the kind of question you're doing. Or maybe you said, oh, they're a 1-to-1 ratio, so concentration of A is equal to concentration of B, and that's not true here. So that's how you can go wrong, even when the question is super easy. And then finally, you'll just solve for whatever else the question wants from you, and you guys know how to go from concentration to moles to grams, whatever. So let us do this one. Do you think you can do it without me, or would you like to do it together? What do you think? You want to try? Try without me? Okay, try.
I got the lab. I can basically filled all of this.
Yep.
And I've got the
Yeah.
Yeah.
And you filled this as well?
Yeah, I filled
Okay,
online
perfect.
and online and messages in myself. Yeah.
Nice.
Are we gonna do?
We're going to do it either Friday or Monday, just depending on whether I finish teaching before Friday or not, because I want to have the whole weekend to review all the calculation stuff. Okay. Anytime a question says precipitate or precipitation, first we identify the precipitate. Yes, yes. So if you see precipitate or precipitation, identify the Awesome, thank you. Yeah, and now we're just battling. Right. Page 74. It's yeah, the steps are on page 7. And then the first information. This page. Yeah, and we're going to do allow either. No, yeah. In my group, so. I cross my fingers, but it's not okay. Okay. Tuesday, because Tuesdays is for. Is there anyone else who did not get the lab? Was maybe away last day, did not get the lab sheet? Yeah. What do you think that? Oh, hang on. No. KSP. Yeah. Oh, there's 2 blanks. KSP is.
Yeah, no more pencils from there.
I don't know what happens to them. People eat them or something. I have more.
Yeah. Thank you so much.
So we have the molarity of our SO4 2 minus. Did you guys get 3.6 times 10 to the minus 7? Yeah? Okay. What are we going to do with that in order to get our mass of Na2SO4? What else do we need to use from the question? First of all, we don't just want SO4, we want Na2SO4. Is that any different? Is the concentration of Na2SO4 different from the concentration of SO4? Na2SO4 has how many SO4s? One SO4. So there's one SO4, 2 minus for every one Na2SO4. Therefore, concentration of Na2SO4 is going to be the same, right? Because it's 1 to 1. In order to get to mass of Na2SO4, what do we need to find first? Well, we need to find the molar mass, but that's a conversion factor. What do we need to get? What's the step before getting to mass? We want to end at grams. What do we need before we get to grams? Moles. Do we have enough information to get to moles? We have moles per liter. How would we get to moles? How would we get to moles if we have moles per liter? What? We need to cancel the liters. Do we have liters?
Yeah.
Oh my goodness, we do. How lovely. Okay. And then from moles, we can convert to grams. Oops, that was happening down here. And our molar mass is 142.1. is good? Okay. So we've now done 4 out of 5 types of problem. And now we need to do the 5th. And the 5th is different because it does not involve KSP. The 5th is a titration. So we're going to do a little review of titration. And this is on page 76. Okay. This is simply stoichiometry. And stoichiometry you always take whatever you have, you convert it into moles of A, and then you convert it into moles of B, and then you convert that into whatever you need. Yes? So you have whatever information is given about A, you find moles of A. Step 2 is always find moles of B, and then you find whatever you're asked for about B. Steps 1 and 2 are always the same. Find moles, find moles. Find moles, find moles. They're not even different. Find moles of A, find moles of B. And what you're going to be given in a titration, or what you're going to do in a lab for a titration, is you're going to be given a volume of solution A. From that, you can find moles of A using molarity, which is, of course, the moles per liter, to do the conversion. And to go from moles of A to moles of B, what do we use? Moles of one substance to moles of the other substance. We use the mole ratio. Where do you find that? Yeah, that's from the coefficients in the balanced equation. And I'm going to say for titrations, just stop right there for now. Okay, and then you're going to say, what do I need to do next? Because sometimes you'll need to do one thing, sometimes you'll need to do a different thing. Okay, so you're just going to do steps 1 and 2. And then you could be asked to find the mass, you could be asked to find the volume, you could be asked to find the number of particles, or you could be asked to find the concentration. And if you're finding the concentration, that's not a conversion. It is a division, because this is what you had found in the last step, and you would have to divide it by the liters to get the concentration. Okay? So it requires 15.6 milliliters of 2.00 molar H2SO4 to react with a 25 milliliter sample of NaOH. Calculate the concentration of NaOH. Which of these two substances is substance A, the one you can find moles? Is it H2SO4 or is it NaOH? H2SO4, that's going to be substance A. Step 2 is going to be, what will we do next? We will find moles of B. And who is substance B? NaOH. What do we need in order to do that conversion from substance A to substance B? We need the mole ratio, which means we need a balanced equation. So could you guys please write the balanced equation between H2SO4 and NaOH?
The red state, right?
Yes, please. Call me over if you get stuck. Okay, what's one of our products? H2O. What's our other product? Na what? NaSO4? Na2SO4. Very good. And our states, what is the state of H2SO4? Aqueous. NaOH is aqueous. Water is liquid. And Na2SO4 is aqueous. Okay, very good. Are we balanced? No. What do we need to do to balance that reaction? We need a be brave. We need a 2 in front of who? NaOH, yes. We need a 2 there. Do we need a 2 anywhere else? In front of water, yes. Okay, so there we now have our balanced equation. So now that we know we need to find moles of A, we need to find moles of B, we have a balanced equation. Could you guys do that? Could you find moles of A, the H2SO4, and find moles of B? Can you do that? Yep. Okay, go for it.
Stoichiometry won't for graph, but will work for more than
Correct. The mole ratio can only be used for moles.
for both.
It can be used for molecules because molecules are just a smaller form of moles. It can also be used for volumes of gases, but we won't be doing that in grade 12.
What about the concentrations now?
Do use moles. It's just better. Did you get 6.24 times 10 to the negative 3? Yeah? Okay. Once you get to moles of B, you're going to ask yourself, what is the question asking me for? And then you're going to do whatever that question asks you for. The question asks you for concentration of NaOH. And I want you to remember that this is moles of NaOH over liters of NaOH solution. Okay? What is our volume of the NaOH solution?
0.02.
That is our volume of the NaOH solution. That's a good question. Everybody think about that for a moment. If I want the concentration of this sample of NaOH, and I have my moles of NaOH, do I want the moles of NaOH in 25 milliliters and calculate my concentration from that? Or do I want my moles of NaOH in 35.6? Which one makes sense? Why?
Because they both react to each other, so both the meters are combined.
Okay, what was I trying to do in this question? Calculate the concentration of NaOH. How much NaOH is left after the reaction? Zero. Because this goes to completion. So when they ask you for the concentration of NaOH, they're always looking for the initial concentration of NaOH, or whatever it is, because the final concentration will always be 0. When you're doing a titration, you're using up the reactants completely. The point of a titration is that there's no excess of A, there's no excess of B, they react completely, and so your reactant concentrations are 0 at the end of the titration. Therefore, the molarity they're looking for, the concentration they're looking for, is always the initial concentration, because if they asked you for the final concentration, it would always be 0. So we're always going to use the initial volume. And that one there is going to be 0.0250 liters. We get 0.2496. I think we have 3 sig figs there, so that's going to become 0.250 molar NaOH. Do you remember I said never use M1V1 equals M2V2 for titrations? Do you want to see what happens if we do M1V1 equals M2V2? Okay, because it doesn't actually make any sense. Okay, so we would say M1V1, and that's going to be for H2SO4, right? Equals M2V2, and that's for NaOH. Yes? Yeah, that would mean that our moles of H2SO4 was equal to our moles of NaOH. Is it true that moles of H2SO4 are equal to the moles of NaOH? No. Okay. So just don't use it ever. Never for titrations. This is a dilution equation, not a titration equation. Okay. Titration is a little bit like a mix and match, yes. Now, it does have a reaction where you will have things proportional to the coefficients. And it turns out, and this is the really devious part, is that if your mole ratio had been 1:1, that formula would actually give you the correct answer. But it's only going to do it if it is 1:1. And you'll start thinking, oh, this is great. I will always use this, and half the time you'll get it wrong. Yeah, so just don't use it ever for titration and you will be safe, okay? You will sometimes, if you go on ChatGPT or if you go on like some YouTube channels, they'll be like M1V1, M2V2, and they'll use it for a titration. And it is just such a, it's such a deceptive thing because it'll trick you into thinking that it works and it doesn't on a consistent basis. And you don't want to be using something that only works 50% of the time. That would kind of suck. It'd be like if you went to use your car and it only started 50% of the time. You'd be like, well, I got to work, but can't get home. Darn it. Okay. All right. Now, in terms of a titration, we are going to be doing a lab. For this test, you will not be tested on the words. Okay, not tested on the words. But it will be part of Unit 5 because we'll do more titrations in Unit 5. So should we introduce them here while we're here and then you see them again in Unit 5? Yes, because otherwise you're like, oh my God, what are all these words? Okay. So this is a lab procedure and it is called a titration. And it is an effective way to determine the concentration of an unknown aqueous substance by gradually adding one reactant. What's another word for a reactant? Reagent, yes. And it's not reagent, it is reagent. Okay? By gradually adding one of the reagents to a precisely measured volume to the other reagent or reactant, we are going to reach an end point. The end point is when the reaction is perfectly complete and there is no excess of reactant A and no excess of reactant B. What is wrong with the pen? Come back to me, pen. Okay, there's no excess of either reactant.
There's no reaction in general afterwards.
Yeah, just like there's no leftover. You've used it all up and it's all product. One-way arrow and nothing left over. Okay? Now, one of our solutions is going to be our known. That didn't look nice. I'm writing over top of things. Let me try that again. One of our solutions is our known. And that's called our standard solution. Our standard solution has a precisely known molar concentration. So it's our known concentration. That's called our standard. The sample solution is the one where we have an unknown concentration. So when we were looking at that before, this was substance A, and this was substance B. Yeah? There are other words for these things. The standard is also known as the titrant. The sample is also known as the analyte because you analyze it. The standard solution is called the titrant because you titrate the sample with it. And remember, is sample known or unknown? The sample is unknown.
But when it says standard solution, it says known solution.
Known volume, but unknown molar concentration. Okay? You can't know nothing about it, otherwise it doesn't work. Yeah, we have to have enough information that we can solve. Okay? The sample, which is the unknown, is also known as the analyte because it is the solution we are analyzing. What is a burette? Yeah, exactly. That big, long, tall things. They're over there in the corner of the room by the, there's a fire extinguisher and a paper towel dispenser. Right beside that are our burettes. And what do you do with the burette? You turn the little valve, what happens? Drip, 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 drip. Yes? Okay, so drip, drip, drip. And you'll have a starting volume, you'll have a final volume, and then you'll say, what's the difference between those two? Okay? Usually there is going to be an indicator. Okay, how many people did a titration last year? If you did a titration, what color did your solution turn? It turned a bright pink color, and that's because you added a phenolphthalein indicator. And what an indicator does is it changes color when we have perfectly completed the reaction, when we have no excess of either reaction. Okay, so it turns color, changes color, and hopefully it changes color when the reaction is complete. You could actually choose a bad indicator and it would change before the reaction is complete or after the reaction is complete, but that would be because if I chose that, I would have been a bad chemist. Okay, and you can choose a bad indicator, but in a perfect world, you will choose one that changes when the reaction is perfectly complete. I messed up. Damn it. The point where the reaction is perfectly complete is not the end point. The point where the reaction is perfectly complete is called the equivalence point. I'm so sorry. The end point is where the indicator changes color. If you have done a good job of choosing your indicator, those will happen at the same time, which is why I messed it up. And because they both start with E, which is really irritating. So I'm sorry that they both start with E, and they almost seem like the same thing, but they are not. So the equivalence point, that's the point where it has completely reacted and there's no leftover. So that's our equivalence point. Completely reacted, no leftover. It's also known as the stoichiometric point, which means that you have perfectly fulfilled the stoichiometry. If it was a 1-to-2 ratio, you provided one of these and two of those and they reacted completely. Yes? If it was 1-to-1, you provided one of these and one of those and they reacted completely. If it was a 2-to-3, you provided two of these and three of these and they reacted completely. No excess. That is your equivalence point. That is your stoichiometric point. The end point is where the indicator changes color. So end point is to do with the indicator. And it is where the indicator changes color. You should choose your indicator so it happens at the same time as the equivalence point.
So both of them happen at the same time. But
If you've chosen it correctly. So they will happen at the same volume.
so the equivalence point starts at the end point too.
The equivalence point, okay, so let's go back to basics. Equivalence point is where you have reacted everything completely. If you have chosen your indicator correctly, that is the point at which your indicator will change color. Okay? If you chose poorly, your indicator might change color before that or after that. So if you've done a bad job, your endpoint might be over here, your equivalence point is here, right? Your equivalence point might be here and your endpoint might be here. That's bad chemistry. You want your equivalence point to be here and the indicator to change color like right here, okay? Finally, we have an outlier. And I can guarantee when you do your math quiz on this, there will be an outlier on your quiz. Okay? Do you guys know what an outlier is in your data? No. Okay. So what you're going to do is you'll take your sample. Maybe in this case, you've taken some NaOH and you're going to titrate it with HCl. So you drip, 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 and you're like, oh, 10 milliliters, 5 milliliters. You do your calculation and you find a concentration. Do you think you did it perfectly that one time that you did it? Probably not, right? But if you repeat it several times, so you take a new sample and you do it again, drip, 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 drip. Oh, it turned color, yay, you calculate. Now you've done it twice. Now you can take the average of the two, yes? If you're doing it more, the more times you do it, the more accurate you're going to get, yes? The more precise you're going to get, hopefully, all right? So what might happen though is you might calculate your molarity for each of your samples. We call them trials. You try it once, you try it a second time, so it's called a trial. Maybe you've tried it 4 times and 3 of them give you 1 molar and 1 of them gives you 2 molar. The 2 molar is what we call an outlier. It means that, ooh, we screwed up somewhere. Yes? Perhaps we forgot to add the indicator, or I don't know. Like, there's all kinds of ways you could go wrong. You wrote a number down wrong. Yes? That happens, right? So, or maybe you were doing it and you went over the endpoint, like it turned really, really bright pink. It could be. That's an outlier. Should you use the outlier in your average? No. Okay? So usually, the standard solution goes in the burette. The standard solution, what color did I do standard? Standard was blue. Standard solution, that's the one where we know it, goes in the burette. The sample solution, that's our unknown, usually goes down here. And also down in the, what kind of a flask is this called? Erlenmeyer flask.
How we learned about this? Yeah.
Yes. Burette, Erlenmeyer flask. And we add an indicator that also goes into the flask. So our indicator also goes in the flask. And you drip, 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 drip until it changes color. And good data for the purposes of chemistry 12 is within 0.2 milliliters of each other. Okay, anything outside of that is an outlier. And when you have an outlier, you omit it from your calculations. And I am given to understand that omit is a word that is unfamiliar to many people, which if English is your second language, I would not be surprised. You know what I mean? Like there's all kinds of words that like I am like, oh, how could you not have heard of that? But of course, you know, why would you have ever heard that? Anyway, omit means just leave it out. Leave it out. So if you've not heard that before, omit means leave it out. I'm always surprised at the words that people are familiar with. Sometimes I'm like, wow, you know that? This is your second language and you know that? And then other words I'm like, how do you not know that? But then it's like, well, why would you, right? So yeah, it's always kind of like, wow, that's kind of cool. Anyway, so that's what that's about. This shows the procedure. I'm not going to go through that right now. What we are going to do is we are going to go to page 81. And we're going to do this one right now, page 81. We have 25 milliliters of hydrobromic acid, HBr, and it is titrated with a solution of NaOH, and the following data are recorded. So the VI is at when you're nearer the top of the burette. The VF is when you're lower down on the burette. How do we find the V delivered? Like how much was dripped out? Yeah, so how would we calculate that? How would we take our VI and our VF? Yeah, how much was dripped out? The V delivered equals VF minus VI. Okay, so it's done for you here, but if you needed to do it in the future, this is VF minus VI. Okay. One thing you might notice is that if we look here, the final volume of trial 1 is the initial volume of trial 2. You do not need to refill the burette every time, right? You can say, I start here, I finish here, that was trial 1, I can start from here next time. Does that make sense? You just have to make sure you've got enough. Okay, and you'll notice that trial 2, we're down at 32. Oh, it looks like we filled it up again because maybe we were worried we would run out. Okay? So if we take a look at this, which solution was the standard and which solution is the sample? Have a chat with your neighbor about that. First of all, what does standard mean? What is sample? Which is the known and which is the unknown? Oh yeah, absolutely, no worries. Yep. Good stuff. No worries.
Yeah, so I took we put it in ourselves, right? That's how it works. Like hydrogen floating out, I think hydrogen out and get up it. Yeah. Like known is like at the very start, right? Like we can always
Known means known concentration.
do the concentration.
So when we say standard, do we mean known or unknown? Known. And what do we know about it? What is it that is known about the standard? It is the known concentration. That means our sample is of unknown concentration. So we need to know the concentration of one of these two things. Which one do we know the concentration of? The NaOH. It's given to you right there. You might have to look for it, okay? Make sure you look at all your data. If you are given data, look everywhere, right? So our standard is the NaOH because we know its concentration. And that means that our sample is the HBr. When you calculate the average of NaOH used, you should not include the starred trial. Why not? So out of all of our trials, those 4 purple values, we're not going to use 16.28. Why not? It is an outlier. All the rest of the data is within how much? 0.2 milliliters. $16.28 is, I don't know, 0.5 from the closest volume. So we will leave it out of our calculations. So now you are going to calculate the average volume of NaOH needed to neutralize the HBr.
Wait, include the first excluding.
Exclude the first one because it is the outlier. And because we're not done with our calculations yet, I'm going to throw on a couple extra digits just so I don't end up with a rounding error later. And I want you to look at your work and say, would I lose a half a mark for not having milliliters? Or would I get my mark for having milliliters? Okay, make sure you've got your milliliters in your work and in the answer. Okay? And now you are going to use the average volume of NaOH to calculate the concentration of the HBr. Give it a try. Remember, step 1 is find moles of A. 2, find moles of B. Step 3, find whatever you're asked for. If you're stuck, write down everything that you know about the NaOH. Go back to the question and be like, what do I know about the NaOH? I know that there are 15.7733 milliliters. Do I know anything else? I know its molarity. Yes, I do. I know it is 0.500 molar. Do I know anything about HBr? Oh, I know the volume of HBr. I know that there are 25 milliliters. So I'm going to use that information and let's see if you can do it. Yeah, you'll need an equation. Yep. For acids and bases, there's two ways to balance it. You can leave this as HOH and balance your OHs and your H's, which shows you that it's already balanced, right? Or you can say for every OH, I need an H. For every OH and H, I need a water. So if I've got one OH and one H, I'm going to get one water. And then the Na you can just look at and be like, oh, there we go. It's all 1 to 1 to 1. So this is a really easy one. And just in case you're wondering, actually, you don't have to stop at moles of NaOH. You could go straight to moles of HBr all in one line. Oh, look. You could be like, oh, and then there's one HBr for every one NaOH, yes? You could do it in 2 steps, or you could just show it all in one line. Either way is fine. I would like to know, we're doing our HBr down here, concentration of HBr. On the bottom, what liters am I going to use? Am I going to use 25 milliliters? Am I going to use 15.77 milliliters? Or am I going to use those two added together? 25? 15.77? Or both of them added together? 25. Remember, you're always using the initial volume, and it's for HBr, so this is my volume of HBr, and the volume of HBr is 25 milliliters. Yes? This is my initial volume of HBr. Okay? I don't know what the answer is. Yes, I do. It's right here. There we go. Okay. I don't know if that's the right sig figs. It looks like it shouldn't be, because we've got a 3 sig fig thing, so that should be, I should fix this. So for homework, you guys could do page 75, number 1, 2, 3. And page 79. Page 79, number 2 and 3. There you go.